Assalamualaikum and hi. We are going to discuss a few things about ordinary differential equations. First of all, what is differential equation? An ordinary differential equation is an equality involving a function and its derivatives. An ODE of order n is an equation form. This is the equation form where y is a function of x, y prime equal to dy over dx is the first derivative with respect to x, and y to the power of n equal to d to the power of ny over dx to the power of n is the n derivative with respect to x. Involve only one independent variable. For example, dy over dx plus 5y equal to exponent x, d square y over dx square minus dy over dx plus 6y equal to 0. Next is properties or characteristic of ODE. The first one, existence is when at least one solution can be determined for a given problem, while uniqueness is the property of being the only possible solution. One of the most important theorem in ODE is Picard's existence and uniqueness theorem for first-order ODE. Why is Picard's theorem so important? One reason is it can be generalized to establish existence and uniqueness result for higher-order ODE. The method to find y is known as the method of successive approximations or Picard's iteration method. This is how it goes. Step 1. Consider the constant function y naught x equal to y naught. For step 2, once the function y and x is known, we define this function. For step 3, by induction, we generate a sequence of function y and x which, under the assumption made on fxy, converge to the solution yx of the initial value problem, y prime equal to fxy, yx naught equal to y naught. For a second order ordinary differential equation, this is the equation. Next is the solution of differential equation. The first one is the purpose of adding constant. The key concept to note here is that when you differentiate a constant, you get 0. This is due to the fact that the slope of the tangent line of a constant function, say fx equal to 4, will simply be a horizontal line spanning the x-axis with a slope 0 everywhere. For the simplest differential equation, y prime equal to ft, this is the general solution for definite integral of ft equal to ft plus c. We have to make sure the equation is in the standard form, which is y prime plus pt y equal to gt. If the leading coefficient is not equal to 1, we have to divide the equation through by the coefficient of y prime. For example, if the coefficient is 2, so we have to divide the whole equation by 2. When we make sure the equation is in the standard form like this, we can find the integrating factor by function mu t equal to exponent to the power of pt dt. Next, we can find the solution yt equal to Next, we can find the solution by yt equal to integrate mu t gt dt plus c over mu t. Always remember to include the constant of integration which is included in the formula above as plus C at the end. For separable differential equation, for example, when we are given this equation can be written as this equation by multiplying both sides with y. Now we can easily identify gy and fx of equation 1, which is this equation. When we go back to the general case, we can rewrite this equation 1 as equation 2a or even as equation 2b. In our example equation, we will use example 2b for our equation. Next, we have to integrate both sides and we will get this equation, which is the equation for the family of ellipse. Don't forget to add the c constant. If we forget the integration constant c, then the equation will be 9/2 y square plus 2x square equal to 0. This equation has only one real solution for x equal to y equal to 0 and describe the origin 0, 0. For linear differential equation, for first order, this is the equation. We know that the constant of integration c is unknown constant.
Next is homogeneous linear equation with constant coefficient for second order. Okay, this is our equation for a second order homogeneous equation with constant coefficient where a, b and c are constant. Next is homogeneous linear equation with constant for higher order, and this is our equation regarding to this higher order of homogeneous linear equation. Number 4 is the method to solve ODE. Okay, the first method is separation of variable for the first order. This method only possible if we can write the differential equation in the form of ax dx plus by dy equal to 0, where ax is a function of x only and by is a function of y only. Once we can write it in the above form, then we can integrate to obtain our general solution. We only deal with first order, first degree differential equation. The example for the separation of variable. When we are giving this equation, we want all x on one side, all the term t in the other side. Then we divide both sides by x plus 3 and multiply both sides by dt. And next we divide both sides by t, and then we can integrate both sides. Dx and dt must be on top of the fraction to make integrate. After we integrate this equation, we will get the new equation. We will get the answer, and we will take exponential to power of both sides because we want to eliminate 1, and we will get the answer is equal to kt, where we let exponential power of c is equal to k, where is k is the constant, and we will get the answer is x equal to kt minus 3. Second is integrable combination for the first order. There are many differential equations where we cannot separate the variables. However, we can solve the equation if we use one of the following equation in a form that we can solve, such as equation 1, 2, 3 and 4 Romans. These differential form are called integrable combination. For the first equation, it comes from the product rule, while the second expression comes from the implicit differentiation and related rates, while 3 and 4 Roman comes from the quotient rule. The example of the integrable combination is our equation. First, we note that we cannot separate the variable, such as that the x expression would be with dx only and the y expression would be with dy only. So dE is not separable. Okay, so we aim to get the dE in one of the integrable combination form, and we rearrange this equation to form the new equation. Okay, from the integrable combination, the expression in bracket can be written as dxy. This combination we will written as dxy, and we will form the new equation with dy 2y dy plus dxy equal to 0. After we get this differential equation, we will integrate this equation and it will lead this answer, and we call it the general solution. Okay, to check the general solution is correct or not, now we are using implicit differentiation and product rule and d per dx multiplied by k is equal to 0. So putting this together give the derivative of our answer as this. On multiplying by dx, we will have this our new equation with the e that we start with. We know the general solution is correct because this equation is not separable, because x dy cannot be separate to the x term and y term, and y dx cannot be separate, and we know that the general solution is correct. Linear dE of first order. If p equal to px and q equal to qx are function of x only, then we will obtain dy over dx plus py equal to q, called linear differential equation of first order. We can solve this linear differential equation by using an integrating factor. Okay, next is Euler's method, a numerical solution for the first order. When we cannot solve the equation using the technique separation of variables, integrable combination, or integrating factor, we can use the Euler's method because a numerical approach gives us a good approximate solution. The general initial value problem, which is IVP, we are trying to solve problems that are present in the following way: dy over dx equal to fxy and y, the initial value is known, where fxy is some function of variable x and y that are involved in the problem, and is our example of the IVP. And note that the right hand side is a function of x and y in each case. Euler's method can return in the form of Taylor series and is form of the Taylor series, but in Euler's method we just take the first two terms only, which is y x plus h y prime x, and the last term is just h times our dy dx expression, and it will lead this our Euler's method equation. Next is Ranji-Kutta RK4 numerical solution for differential equation. Okay, the problem with Euler method use is to solve a small interval size to get reasonable accurate result. That is not very efficient, but in the Ranji-Kutta method produce a better result in fewer steps. Okay, this is our formula of Ranji-Kutta method, whereas F1 is represent represented by this function, this equation, f2, this equation, f3, and f4. And we will using this formula to solve. Next is the other method is linear multi-steps methods, general linear methods, collocation method, Galerkin methods. And that's all from us. Thank you.